Greetings everyone, my name is Gigi and this is Let's Build, where I build a Lego set timed to different media and talk about facts concerning the topic of the build. Today's build is the Lego Technic NASA Apollo Lunar Roving Vehicle versus Pretty Soldier Sailor Moon. All footage I am using is for science, educational, and research purposes. My content is transformative and protected under fair use. All footage is time-lapse with commentary. I apologize in advance for pronouncing names or places incorrectly. Spoilers ahead, you've been warned. Specifications for the Lego set. Embark on a journey to the moon with this detailed Lego Technic NASA model set for adults. The set includes a displayable model version of the Lunar Rover Vehicle, carried by Apollo 17 plus 3 attachable equipment sets. Unfold the NASA rover, add the equipment and test out the steering and suspension while imagining what it would be like to complete moonwalks and gather lunar samples. Check out the model battery pack, which includes heating and cooling elements, plus a TV camera with antenna. Explore the communications unit, try out tools that include a shovel and drill, and find Lego moon rock elements. The set also features the Traverse Gravimeter experiment carried by Apollo 17, plus a tribute to Big Mooley, the largest rock sample to have been brought to Earth by the Apollo program. This detailed set makes a dramatic display piece and is a great gift for any adult who enjoys immersive building projects and outer space vehicle models. Build a realistic Lego Technic Lunar Rover model. This LRV building kit for adults is packed with authentic details including seats, steering, suspension, and scientific tools. NASA rover model for adults. Enjoy a mindful project, assembling all the details of the rover and equipment including the battery pack, heating and cooling elements, and the comms unit. A build for NASA fans. Remember the Apollo 17 mission with a display that features the Lunar Roving Vehicle alongside 3 detailed equipment attachments, each with its own information plaque. Essential equipment. This set comes with a greater insight into the Apollo missions and comes with a wealth of accessories including comms equipment, tools for collecting lunar samples, and much more. A gift for adults who love NASA and outer space. This set makes a great gift idea to inspire space fans to learn more about the Apollo missions. Engaging building instructions. Blast off on a rewarding building adventure with the Lego Builder app, where you can save your sets and track your progress. Measurements. 1,913 piece set with a model measuring over 5.5 inches high, 15 inches long, and 10 inches wide. To the moon and back. Since the first humans set foot on the moon in 1969, our exploration of space has yielded new knowledge of the universe that few could have ever imagined. Early explorations of the moon, pioneered by NASA's Apollo missions, opened a gateway to innovative technology and extraordinary missions further and further into our solar system. This Lego Technic model is inspired by NASA's Apollo 17 Lunar Rover Vehicle, the LRV-3. The rover was a remarkable feat of engineering and exploration, and, as a part of NASA's final Apollo mission, it played a pivotal role in pushing the boundaries of lunar exploration. Explore your LRV-3. Astronauts completed several expeditions in the LRV-3 to collect rock and soil samples and capture breathtaking images of our closest celestial neighbor. Explore intricate details as you build. Said by Olav Grøygaard, Lego Technic designer. Details on display. Like its original counterpart, your Lego LRV-3 rover can be folded neatly to fit inside an actual lunar lander module for transportation to the moon. The final model can be displayed as one or in separate sections. Forward chassis. A compass only works with the Earth's magnetic fields. So astronauts used a directional gyro and odometer to navigate the moon's surface. Moon dust would get everywhere, and a cleaning brush, though not a typical scientific tool, was essential to keep radiators, TV cameras, and the rover surface clean. Lunar Communications Relay Unit, the LCRU. The Lunar Communications Relay Unit was the most important communications link for astronauts during extravehicular activities to the moon. The high and low gain antennas connected astronauts with Houston Mission Control Center. Aft pallet assembly. Astronauts conducted a series of scientific experiments, including active and passive seismic activity and profiling, while using and storing tools and samples on the aft pallet assembly. The Lego rock in the back represents Big Mooley, a 4-billion-year-old rock collected by Apollo 16. The Lunar Roving Vehicle, LRV, is a battery-powered, four-wheeled rover used on the moon in the last 3 missions of the American Apollo program, 15, 16, and 17, during 1971 and 1972. It is popularly called the moon buggy, a play on the term dune buggy. Built by Boeing, each LRV has a mass of 462 pounds without payload. It could carry a maximum payload of 970 pounds, including 2 astronauts, equipment, and cargo such as lunar samples, and was designed for a top speed of 6 miles per hour, although it achieved a top speed of 11.2 miles per hour on its last mission, Apollo 17. Each LRV was carried to the moon folded up in a lunar module's Quadrant 1 bay. After being unpacked, each was driven an average of 20 miles without major incident. The last 3 LRVs remain on the moon. History. The concept of a lunar rover predated Apollo, with a 1952 to 1954 series in Collier's Weekly, a magazine by Wernher von Braun and others. Man will conquer space soon. In this, von Braun described a 6-week stay on the moon, featuring 10-ton tractor-trailers for moving supplies. In 1956, Mieczysław G. Becker published 2 books on land locomotion while he was a University of Michigan professor and consultant to the U.S. Army Tank Automotive Command's Land Locomotion Laboratory. The books provided much of the theoretical basis for future lunar vehicle development. In 1959, George von Tysenhausen conceived the lunar rover as a 4-wheel drive vehicle with non-inflated flexible wheels. Early lunar mobility studies. In February 1964 issue of Popular Science, von Braun, then director of NASA's Marshall Space Flight Center, discussed the need for a lunar surface vehicle and revealed that studies had been underway at Marshall in conjunction with Lockheed, Bendix, Boeing, General Motors, Brown Engineering, Grumman, and Bell Aerospace. Saverio Morea was named LRV manager at MSFC in 1961. Beginning in the early 1960s, a series of studies centering on lunar mobility were conducted under Marshall. This began with the Lunar Logistics System, followed by the Mobility Laboratory, then the Lunar Scientific Study Module, and finally the Mobility Test Article. In early planning for the Apollo program, it had been assumed that 2 Saturn V launch vehicles would be used for each lunar mission, one for sending the crew aboard the Lunar Surface Module to lunar orbit, landing and returning, and a second for sending LSM truck with all of the equipment, supplies, and transport vehicles for use by the crew while on the surface. All of the first Marshall studies were based on this dual launch assumption, allowing a heavy, large roving vehicle. Grumman and Northrop in late 1962 began to design pressurized cabin vehicles, with electric motors for each wheel. At the same time, Bendix and Boeing started their internal studies on lunar transportation systems. Becker, now with General Motors Defense Research Laboratories at Santa Barbara, California, was completing a study for NASA's Jet Propulsion Laboratory on a small, uncrewed lunar roving vehicle for the Surveyor program. Fenrik Pavlik, originally from Hungary, used a wire mesh design for resilient wheels, a design that would be followed in future small rovers. In early 1963, NASA selected Marshall for studies in the Apollo Logistics Support System. Following reviews from all earlier efforts, this resulted in a 10-volume report. Included was the need for pressurized vehicle in the 6,490 to 8,470 pound weight range, accommodating 2 men with their expendables and instruments for traverses up to 2 weeks in duration. In June 1964, Marshall awarded contracts to Bendix and Boeing, with GM's lab designated as the vehicle technology subcontractor. Bell Aerospace was already under contract for studies of lunar flying vehicles. Even as the Bendix and Boeing studies were underway, Marshall was examining a less ambitious surface exploration activity, the LSSM. This would be composed of a fixed, habitable shelter laboratory with a small lunar traversing vehicle that could either carry 1 man or remotely be controlled. This mission would still require a dual launch with the Moon vehicle carried on the lunar truck. Marshall's Propulsion and Vehicle Engineering Lab contracted with Hayes International to make a preliminary study of the shelter and its related vehicle. Because of the potential need for an enclosed vehicle for enlarged future lunar explorations, those design efforts continued for some time and resulted in several full-scale test vehicles. With pressure from Congress to hold down Apollo costs, Saturn V production was reduced, allowing only a single launch per mission. Any roving vehicle would have to fit on the same lunar module as the astronauts. In November 1964, 2 rocket models were put on an indefinite hold, but Bendix and Boeing were given study contracts for small rovers. The name of the Lunar Excursion model was changed to simply Lunar Module, indicating that the compatibility for powered excursions away from a lunar lander base did not yet exist. There would be no mobile lab. The astronauts would work out of the LM. Marshall also continued to examine uncrewed robotic rovers that could be controlled from the Earth. From the beginnings at Marshall, the Brown Engineering Company of Huntsville, Alabama, had participated in all of the lunar mobility efforts. In 1965, Brown became the prime support contractor for Marshall's P&VE laboratory. With an urgent need to determine the feasibility of a 2-man self-contained lander, von Braun bypassed the usual procurement process and had P&VE's Advanced Studies Office directly task Brown to design, build, and test a prototype vehicle. While Bendix and Boeing would continue to refine the concepts and designs for a lander, test model rovers were vital for Marshall human factor studies involving spacesuit-clad astronauts interfacing with power, telemetry, navigation, and life support rover equipment. Brown's team made full use of the earlier small rover studies, and commercially available components were incorporated whenever possible. The selection of wheels was of great importance, and almost nothing was known at the time about the lunar surface. The Marshall Space Sciences Laboratory, SSL, was responsible for predicting surface properties, and Brown was also prime support contractor for the lab. Brown set up a test area to examine a wide variety of wheel surface conditions. To simulate Pavlik's resilient wheel, a 4-foot diameter inner tube wrapped with nylon ski rope was used. On the small test rover, each wheel had a small electric motor, with overall power provided by standard truck batteries. A roll bar gave protection from overturning accidents. In early 1966, Brown's vehicle became available for examining human factors and other testing. Marshall built a small test track with craters and rock debris where several different mock-ups were compared. It became obvious that a small rover would be best for the proposed missions. The test vehicle was also operated in remote mode to determine characteristics that might be dangerous to the driver, such as acceleration, bounce height, and turnover tendency as it traveled at higher speeds and over simulated obstacles. The test rover's performance under 1/6 gravity was obtained through flights on a KC-135A aircraft in a reduced gravity parabolic maneuver. Among other things, the need for a very soft wheel and suspension combination was shown. Although Pavlik's wire mesh wheels were not initially available for the reduced gravity tests, the mesh wheels were tested on various soils at Waterways Experiment Station of the U.S. Army Corps of Engineers in Vicksburg, Mississippi. Later, when wire mesh wheels were tested on low-G flights, the need for wheel fenders to reduce dust contamination was found. The model was also extensively tested at the U.S. Army's Yuma Proving Ground in Arizona, as well as the Army's Aberdeen Proving Ground in Maryland. Lunar Roving Vehicle Project. During 1965 and 1967, the Summer Conference on Lunar Exploration and Science brought together leading scientists to assess NASA's planning for exploring the Moon and to make recommendations. One of their findings was that the LSSM was critical for a successful program and should be given major attention. At Marshall, von Braun established a Lunar Roving Task Team, and in May 1969, NASA approved the Manned Lunar Rover Vehicle program as Marshall Hardware Development. The project was led by Aberhard Rees, Director of Research and Development at Marshall, who oversaw the design and construction of the rover, with Savero Morea acting as project manager. On July 11, 1969, just before the successful moon landing of Apollo 11, a request for proposal for the final development and building of the Apollo LRV was released by Marshall. Boeing, Bendix, Grumman, and Chrysler submitted proposals. Following 3 months of proposal evaluations and negotiations, Boeing was selected as the Apollo LRV prime contractor on October 28, 1969. Boeing would manage the LRV project under Henry Kudish in Huntsville, Alabama. Kudish was replaced the following year in 1970 by LRV project manager Earl Houts as a major subcontractor. The General Motors Defense Research Laboratories in Santa Barbara, California, would furnish the mobility system, wheels, motors, and suspension. This effort would be led by GM program manager Samuel Romano and Pavlik's. Boeing in Seattle, Washington, would furnish the electronics and navigation system. Vehicle testing would take place at the Boeing facility in Kent, Washington, and the chassis manufacturing and overall assembly would be completed at the Boeing facility in Huntsville. The first cost-plus incentive fee contract to Boeing was for $19 million and called for delivery of the first LRV by April 1, 1971. Cost overruns, however, led to the final cost of $38 million, which was about the same as NASA's original estimate. 4 lunar rovers were built, each one for Apollo's missions 15, 16, and 17, and one used for spare parts after the cancellation of further Apollo missions. Other LRV models were built: a static model to assist the human factors design, an engineering model to design and integrate the subsystems, 2 1/6 gravity models for testing the deployment mechanism, 1 gravity trainer to give the astronauts instruction in operation of the rover and allow them to practice driving it, a mass model to test the effect of the rover on LM structure, balance, and handling, a vibration test unit to study the LRV's durability and handling of launch stresses, and a qualification test unit to study integration of all of the LRV subsystems. A paper by Morea gives details of the LRV system and its development. LRVs were used for greater surface mobility during the Apollo J-class missions, Apollo 15, 16, and 17. The rover was first used on July 31, 1971, during the Apollo 15 mission. This greatly expanded the range of the lunar explorers. Previous teams of astronauts were restricted to short walking distances around the landing site due to bulky spacesuit equipment required to sustain life on the lunar environment. The range, however, was operationally restricted to remain within walking distance of the lunar module in case the rover broke down at any point. The rovers were designed with a top speed of about 8 miles per hour, although Eugene Cernan recorded a maximum speed of 11.2 miles per hour, giving him the unofficial lunar land speed record. The LRV was developed only in 17 months and performed all its functions on the Moon with no major anomalies. Scientist astronaut Harrison Schmitt of the Apollo 17 said, "Lunar rover proved to be the reliable, safe, and flexible lunar exploration vehicle that we expected it to be. Without it, the major scientific discoveries of Apollo 15, 16, and 17 would not have been possible, and our current understanding of lunar evolution would not have been possible." The LRVs experienced some minor problems. The rear fender extension of the Apollo 16 LRV was lost during the mission's second extravehicular activity at Station 8 when John Young bumped into it while going to assist Charles Duke. The dust thrown up from the wheel covered the crew, the console, and the communications equipment. High battery temperatures and resulting high power consumption ensued. No repair attempt was mentioned. The fender extension on the Apollo 17 LRV broke when accidentally bumped by Eugene Cernan with a hammer handle. Cernan and Schmitt taped the extension back in place, but due to the dusty surfaces, the tape did not adhere, and the extension was lost after about 1 hour of driving, causing the astronauts to be covered with dust. For their second EVA, a replacement fender was made with some EVA maps, duct tape, and a pair of clamps from the inside of the lunar module that were nominally intended for the movable overhead light. This repair was later undone so that the clamps could be taken inside for the return launch. The maps were brought back to Earth and are now on display at the National Air and Space Museum. The abrasion from the dust is evident on some portions of the makeshift fender. The color TV camera mounted on the front of the LRV could be remotely operated by mission control, in pan and tilt axes, as well as zoom. This allowed far better television coverage of the EVA than earlier missions. On each mission, at the conclusion of the astronauts' stay on the surface, the commander drove the LRV to a position away from the lunar module so that the camera could record the ascent stage launch. The camera operator in mission control experienced difficulty in timing the various delays so that the LM ascent stage was in frame through the launch. On the third and final attempt, the Apollo 17 mission, the launch and ascent were successfully tracked. NASA's rovers left behind are among the artificial objects on the Moon, as are the Soviet Union's uncrewed rovers, Lunokhod 1 and Lunokhod 2. Features and specifications. The Apollo Lunar Roving Vehicle is a battery electric vehicle designed to operate in the low-gravity vacuum of the Moon and to be compatible with traversing the lunar surface, allowing the Apollo astronauts to extend the range of their surface vehicular activities. 3 LRVs were used on the Moon. one from Apollo 15 by astronauts Dave Scott and Jim Irwin, one from the Apollo 16 with John Young and Charles Duke, and one from the Apollo 17 mission by Eugene Cernan and Harrison Schmitt. The mission commander served as the driver, occupying the left-hand seat of each LRV. Features are available in papers by Moria, Baker, and Kudish. Mass and payload. The lunar roving vehicles have a mass of 460 pounds and were designed to hold an additional payload of 510 pounds. This resulted in weights in the approximately 1/6 g on the lunar surface of 77 pounds force empty and 160 pounds force fully loaded. The vehicle frame is 10 feet long and has a wheelbase of 7.5 feet. The height of the vehicle is 3.6 feet. The frame is made of 2219 aluminum alloy tubing welded assemblies and consisted of a 3-part chassis that was hinged in the center so it could be folded up and hung in the Lunar Module Quadrant 1 bay, which was kept open to space by omissions of the outer skin panel. They have 2 side-by-side foldable seats made of tubular aluminum with nylon webbing and aluminum floor panels. An armrest was mounted between the seats, and each seat had adjustable footrests and Velcro-fastened seat belt. A large mesh dish antenna was mounted on the mast on the front center of the rover. The suspension consists of a double horizontal wishbone with an upper and lower torsion bars, and damper unit between the chassis and upper wishbone. Fully loaded, the LRV has a ground clearance of 14 inches. Wheels and power. The wheels were designed and manufactured by General Motors Defense Research Laboratories in Santa Barbara, California. Pavliks was given special recognition by NASA for developing the resilient wheel. They consisted of a spun aluminum hub and 32-inch diameter, 9-inch wide tire made of zinc-coated woven 0.033-inch diameter steel strands attached to the rim. Titanium chevrons covered 50% of the contact area to provide traction. Inside the tire was a 25.5-inch diameter titanium bump stop frame to protect the hub. Dust guards were mounted above the wheels. Each wheel had its own electric drive made by Delco, a brushed DC electric motor capable of 0.25 horsepower at 10,000 RPM, attached to the wheel via an 80-to-1 harmonic drive and a mechanical brake unit. In the case of drive failure, astronauts could remove pins to disengage the drive from the wheel, allowing the wheel to spin freely. Maneuvering capability was provided through the use of front and rear steering motors. Each series wound DC steering motor was capable of 0.1 horsepower. The front and rear wheels could pivot in opposite directions to achieve a tight turning radius of 10 feet, or could be decoupled so that only the front or the rear could be used for steering. The wheels were linked in an Ackermann steering geometry, where the inside tires have a tighter turn angle than the outside tires to avoid side slip. Power was provided by 2 36-volt silver, zinc, potassium hydroxide non-rechargeable batteries developed by Eagle Pitcher, with a charge capacity of 121 Ah each, yielding a range of 56 miles. These were used to power the drive and steering motors and also a 36-volt utility outlet mounted on the front of the LRV to power the communications relay unit or the TV camera. LRV batteries and electronics were passively cooled, using the change of phase wax, thermal capacitor packages, and reflective, upward-facing radiating surfaces. While driving, radiators were covered with mylar blankets to minimize dust accumulation. When stopped, the astronauts would open the blankets and manually remove excess dust from the cooling surfaces with hand brushes. Control and navigation. A T-shaped hand controller situated between the 2 seats controlled the 4 drive motors. two steering motors, and brakes. Moving the stick upward powered the LRV forward, left and right turned the vehicle left or right, and pulling backwards activated the brakes. Activating a switch on the handle before pulling back would put the LRV into reverse. Pulling the handle all the way back activated a parking brake. The control and display modules were situated in the front of the handle and gave information on speed, heading, pitch, and power and temperature levels. Navigation was based on continuously recording direction and distance through the use of a directional gyro and odometer, and feeding this data to a computer that would help keep track of the overall direction and distance back at the LM. There was also a sun shadow device that would give a manual heading based on the direction of the sun, using the fact that the sun moved very, very slowly in the sky. Usage. The LRV was used during the lunar surface operations of Apollo 15, 16, and 17, the J missions of the Apollo program. On each mission, the LRV was used on 3 separate EVAs, for a total of 9 lunar traverses or sorties. During operation, the commander always drove, while the lunar module pilot was a passenger who assisted with navigation. An operational constraint on the use of the LRV was that the astronauts must be able to walk back to the LM if the LRV were to fail at any point in time during the EVA, called the walkback limit. Thus, the traverses were limited in distance that they could go at any start and at any time later in the EVA. Therefore, they went to the furthest point away from the LM and worked their way back so that, as the life support consumables were depleted, their remaining walkback distance was equally diminished. This constraint was relaxed during the longest traverse on Apollo 17, based on the demonstrated reliability of the LRV and spacesuits on previous missions. A paper by Burkhalter and Sharp provides details on usage. Deployment. Astronaut deployment of the Lunar Roving Vehicle from the LM's open Quadrant 1 bay was achieved with a system of pulleys and braked reels using ropes and cloth tapes. The rover was unfolded and stored in the bay with the underside of the chassis facing out. One astronaut would climb to the egress ladder on the LM and release the rover, which would then slowly be tilted out by the second astronaut on the ground through use of the reels and tapes. As the rover was let down from the bay, most of the deployment was automatic. The rear wheels folded out and locked into place. When they touched the ground, the front of the rover could be unfolded, the wheels deployed, and the entire frame let down to the surface by pulleys. The rover components locked into place upon opening. Cabling, pins, and tripods would be then removed and the seats and footrests raised. After switching on all of the electronics, the vehicle was ready to back away from the LM. Locations. 4 flight-ready LRVs were manufactured, as well as several others for testing and training. 3 were transported to and left on the Moon via Apollo 15, 16, and 17 missions, and the 4th, LRV-4, was used for spare parts for the first 3 following the cancellation of Apollo 18. The rover used on Apollo 15 was left at Hadley Apennine. The rover used on Apollo 16 was left at Descartes. The rover used on Apollo 17 was left at Taurus Littrow and was seen by the Lunar Reconnaissance Orbiter during passes in 2009 and 2011. In 2020, the state of Washington designated the flown rovers as historic landmarks. Since only the upper stages of the lunar excursion modules could return to lunar orbit from the surface, the vehicles along with the lower stages were abandoned. As a result, the only lunar rovers on display are the LRV-4, the test vehicles, trainers, and mock-ups. Pretty Soldier Sailor Moon is a side-scrolling beat-em-up arcade game developed by Gazelle and released on March 22, 1995. It was published by Banpresto. It is the first game to be created by Gazelle, one of the offshoots of a defunct developer, Toaplan, that were founded after they declared bankruptcy in 1994, and one of the few titles based on Naoko Takeuchi's Sailor Moon shōjo manga and anime series that had official international release. And it also has been compared with other titles in the same genre such as Capcom's Final Fight and Technōs Japan's Double Dragon. Following the first season of the anime series, which adapted the first arc of the manga, the players control one of the 5 original inner senshi, or sailors, and fight against enemies across several locations in order to protect the Earth from the Dark Kingdom, a group of antagonists led by Queen Beryl, who previously destroyed the ancient Moon Kingdom as they attempt to steal life energy from humans and the silver crystal to free Queen Materia from her imprisonment. Takeuchi supervised the production of the project, and voice actors from the anime series returned to reprise their roles, with the mangaka and knuckle-bash designer Junya Inoue serving as one of the game's graphic designers. Gameplay. As with previously released Sailor Moon titles on Mega Drive and Super Famicom, Pretty Soldier Sailor Moon is a side-scrolling beat-em-up game where players take control of the 5 original Sailor soldiers across 8 stages, each one set in a different location, and fight against an assortment of enemies and villains from the series in order to defeat Queen Beryl and the Dark Kingdom. Similar to Golden Axe, each soldier has a special attack of their own that deals damage to all enemies on screen at once, depending on the number of crystals collected along the way, which up to a dozen can be fought at one time. These special attacks also trigger special animations for each of the soldiers, depending on the number of crystals used as well. Unlike other titles based on the franchise, most of the fighting is physical rather than magical, and the soldier can run and perform dashing attacks. Each soldier also has different attributes during gameplay, encouraging players to select their preferred character. At certain difficult points in the battle, Tuxedo Mask will show up and throw a rose, which is a bonus drop that restores health for the players and damages the enemies as well. Stages. Azabu Juban. The Senshi fought against the Yuma in the street with townhouses. Castor and Pollux were the level bosses. Usa P. The Senshi fought their way through the streets of the business quarter. Fruit's Parlor Crown appeared in the background. When they reached the Osa P jeweler's shop, they walked inside and found Naru being strangled by Morga, disguised as Naru's mother. She transformed back into her Yuma form to become the boss enemy. This stage was followed by a cutscene where Queen Beryl and Jedite talked in her throne room. Tokyo Tower. The Senshi fought through back alleys before they met the boss enemy Kurene in a junkyard. When her health was halfway depleted, she would fly away to Tokyo Tower. The Senshi would follow her and fight her there. Crystal Seminar. The Senshi fought in the halls of the Crystal Seminar Cram School. Midway, they fall down into the cellar where they rescued students trapped in shape ray pods. Finally, they reach the computer room from episode 8, where the boss enemy Garoben had captured Umino. Docks. The battle took place on the docks from episode 33. Aside from the usual Yuma, the Senshi had to fight against possessed humans. Zoisite was the final boss. When his health was halfway depleted, he would escape and the stage would end. Nephrite's Mansion. The Senshi went through a forest before they reached the mansion where Nephrite asked the stars for advice in the anime. However, the boss enemies were twin Kurine. Game Center Crown. Anohara was holding her cat Rhett Butler when Zoisite appeared and turned the cat into Bakane. The Senshi chased Bakane through Game Center Crown, where Motoki was watching, and a supermarket where the battle concluded in the streets. When Bakane was defeated, he would turn back into Rhett Butler and reunite with his owner. D-Point. The Senshi fought at the North Pole. Halfway through the stage, Zoisite and Kunsite appeared as mini-bosses in the tunnel from episode 44. Queen Beryl was the final boss and had to be fought in her throne room. There's no final cutscene when the game was won, just the credits. Development and release. Pretty Soldier Sailor Moon was the first title to be developed by Gazelle, which was one of the offshoot companies formed after the closure of Toaplan due to bankruptcy, along with Cave and Takeuchi Corporation. Sailor Moon author Naoko Takeuchi was involved during production as supervisor, and voice actors from the anime series returned to reprise their respective roles. Mangaka and Knuckle Bash designer Junya Inoue was involved during its production as one of the graphic designers. There are 2 versions of the game released. Prior to launch, it was showcased in a playable state to attendees at the 1994 Amusement Machine Show. The second machine fixes a bug with the boss battle against Tuxedo Mask. Reception and legacy. In Japan, Game Machine listed Pretty Soldier Sailor Moon on their May 1st, 1995 issue as being the 11th most successful arcade game of the month, outperforming titles such as Virtua Fighter. Spanish magazine Games Tech praised the visuals. In a retrospective review, Todd Ciolek of Anime News Network criticized several aspects such as the lack of sub-weapon and length. J.A. Larock of Obsolete Gamer gave an overall mixed review of the game, criticizing the music and sound effects, while regarding it as a rip-off of Final Fight, with little girls in school uniforms. Kotaku included it among the best-looking beat-em-up games from the 16-bit era. Argentinian website Malditos Nerds ranked it as number 2 on their top Sailor Moon games. Time Extension included the game on their top 25 best beat-em-ups of all time list. While testing the controls for the game, I opened an action cutscene for Sailor Moon with her crying, which I did not replicate for the recorded play. This was clearly one of those games designed to eat your coins at arcades. I agree with the criticism of this game being too short, with overly simplistic gameplay, and I would also add that some of the enemies are a little unfair, being unable to land hits even when my character is on the same plane. As far as being a franchise tie-in, however, it is better than nearly all LJN games from that era, so I can see fans of Sailor Moon enjoying it. The only note I have for the Lego set is that it would have been a fun idea to make the 3-in-1 Creation Astronaut set to be able to fit comfortably in the rover as a loose collaboration. Total time, 6 hours, 45 minutes, 16 seconds, which means you could watch roughly 20 episodes of Sailor Moon at 20 minutes each. Let me know what you think in the comment section below. Remember to like, subscribe, share, ring that bell, all the things for the YouTubes. Thank you.